In the earlier series of lecture, we have seen the chemistry of elements of first transition series. In the second half, we are going to learn about the chemistry of elements of second and third transition series. My today's lecture is divided into following parts. We are going to learn about the elements of second and third transition series, their position in the periodic table, electronic configuration, and some of the general properties and uses and applications of these transition metal ion into day-to-day life. The first question comes in our mind is that whether the chemistry of second and third transition series elements is similar to that of first transition series, which we have already learned, or there is a difference between these two. The answer to this question is, of course, the chemistry of second and third transition series is bit different than their congeners, that is to say first transition series metal ion. Let us consider one example. Cobalt do form complexes in +2 oxidation state. However, in the same group, rhodium and iridium are placed, and the complexes of rhodium in +2 oxidation state are very few, and that of iridium is almost unknown. So, therefore, do we mean to say that the chemistry of second and third row transition element is completely different than that of the first row? It is not the case. Say for example, a rhodium form complexes in 3 oxidation state, which are very much similar to the congeners, that is cobalt in +3 oxidation state. After understanding this, let us see what about the abundance of second and third row transition element in the earth crust. Compared to the first row transition element, of course, the abundance in the earth crust is very less. One of the element of these two series, that is technetium, does not occur at all in the nature, and it is prepared in the laboratory. In fact, it is the first man-made element into the laboratory. Of the last 6 elements in the second and third rows, that is to say technetium, ruthenium, rhodium, palladium, silver, cadmium, rhenium, osmium, iridium, platinum, and gold and mercury, none occurs to extent of more than 0.16 parts per million in the earth crust. So, if the abundance of these metal ion into the earth crust is very less, does this mean that they are not having useful property? The answer is of course no. Some of the metal ion are very precise, and at the same time they find many applications. Platinum group of metal, say for example platinum, is used widely in the field of catalysis in many industrial processes. Because of this, we have to learn the chemistry of second and third row transition metal ion. So, now let us see in the periodic table how they are placed. This is the complete periodic table, in which just below the first row transition metal ion, the two series starting with the first element, that is yttrium to cadmium, we have a second series, and the first element is lanthanum and the second is hafnium, and then hafnium to mercury, we have a third transition series. This is the general electronic configuration of the second and third row transition series. You will find that the electronic configuration of second and third row transition metal ion are not very similar to those of first row transition series, although they are belongs to the same group in a periodic table. As we know, the transition series is starting from third group to 12th group in a periodic table, and therefore, they are the congeners or belonging to the same group of a periodic table, and therefore, should have a similar electronic configuration. But there are some differences between the first row and that of second and third row transition metal ion. As I said, we have a two groups of 10 elements in each constitutes the second and third row transition series. In this series, the electron is going to fill successively into the 4d and 5d orbital respectively as we move from left to right in the periodic table. The electronic configuration of a first row transition element is quite regular and the 3d orbital is successively filled by 1 electron except at chromium and copper, which is having an anomalous electronic configuration. For the second and third transition series, this regularities in the electronic configuration is not found. There are evidently some pronounced irregularities in the configuration of these elements. Like chromium and copper, the electronic configuration of molybdenum, silver, rhenium and that of gold can be easily understood on the basis of the higher stability of either exactly half filled or full filled d orbital. In all these cases, d orbital is either completely half filled or fully filled, and therefore, this electronic configuration can be understood. However, this concept cannot explain the anomalous electronic configuration of niobium, ruthenium, rhodium, palladium, tungsten and platinum. As a matter of fact, no simple explanation for such anomalies can be offered. There are two factors which play a significant role in determining this configuration. These are electron nuclear attraction and electron-electron repulsion. After understanding the electronic configuration of second and third row transition metal ion, let us now understand the general properties and some of the applications as well as some compounds of these transition series. As I said, we have a triads comprises of 3 elements in each group of a periodic table. In the first group, let us have zirconium and hafnium. Like titanium, both zirconium and hafnium are metal. They are hard and corrosion resistant and their melting point is very high. They are resistant to acid and best dissolve in hydrofluoric acid, where the formation of a anionic fluorocomplex is important and its stabilization of the solution. Zirconium react with air at very high temperature to give a mixture of nitride, oxide and oxonitride. Zirconium is used for cladding and it is also used in the alloy manufacturing. Particularly zirconium niobium alloy is very important superconductor and find applications in superconductivity. The very high absorption of thermal neutrons by hafnium is turned to good use. Hafnium is used to make control rods for regulating the free neutron level in the nuclear reactor used in submarines. Zirconium and hafnium shows oxidation state of +2, +3 and +4, out of which +4 is the most stable oxidation state and therefore, many of the compound of these two metal ion in +4 oxidation states are known. The next group we have a niobium and tantalum. Niobium and tantalum occurs together. Niobium is 10 to 12 times almost more abundant in the earth crust than the tantalum. Niobium and tantalum are silvery colored metal with very high melting point. Pure niobium and tantalum are moderately soft and ductile, but traces of impurities make them harder and brittle. They are extremely resistant to corrosion due to the formation of oxide film on the surface, and at the room temperature they are not affected by air, water or acids other than hydrofluoric acid, which form the complex with this metal ion. Niobium and tantalum both dissolve in fused alkali. Niobium and tantalum do not form positive ion. Thus, though niobium and tantalum are metal, their compounds in +5 state are mostly volatile and readily hydrolyze. Say for example, Nb2O5 and Ta2O5 are amphoteric in nature. They have only weak acidic property. Niobates and tantalates are only formed by fusing it with alkali. Niobium is used in various stainless steel, and niobium steel is used to encapsule the fuel element for some nuclear reactor. A niobium zirconium alloy is a superconductor at low temperature and is used in the wire for very powerful electromagnets. Tantalum is used to make capacitors for the electronic industry, and because of not rejected by the human body, that is to say tantalum is biocompatible metal ion, and therefore it is a valuable for making metal plates, screw and wire for repairing badly fractured bone. So, whenever your bone get damaged, the wire, screw or plates fitted with the tantalum, you should remember the tantalum metal ion at that particular instant. Tantalum carbide is one of the highest melting solids known into the world and having very high melting point around 3800 degree centigrade is for this tantalum carbide. The next group we have a molybdenum and tungsten. Molybdenum and tungsten are also rare. Abundance of both these metal ion in the earth crust is only 1.2 ppm. Both these metal are very hard and very high melting, as well as they are low volatile. The electric conductance of these metal ion is 30% to that of silver. They are extremely refractory, and as I said, they are having very high melting point. As a result of the lanthanide contraction, there is a close similarity in the size and the properties of these metal ion. The difference in property is greater as compared to zirconium and hafnium. Thus, molybdenum and tungsten can be easily separated by using conventional scheme. You might have studied the separation of this metal ion in qualitative analysis. Tungsten belongs to group 1 while molybdenum belongs to group 2, and therefore, we can easily separate molybdenum in form of their sulphide by passing H2S gas in qualitative analysis. The chief use of both this metal in the production of an alloy steel. Even small amount causes tremendous increase in the hardness, and therefore, it is used in high speed steel, which is in fact used in making cutting tool and remaining hard even when it is red heated. Tungsten is also used for filaments used in the lamp. The element give hard, refractory and chemically inert industrial compound with boron, carbon, nitrogen or silicon on direct reaction at very high temperature. Tungsten carbide, say for example, is used for tipping, cutting the tools. The next group we have a technetium and rhenium. Technetium does not occur in the nature, as I said, and it is the first man made element known. All the isotopes of the technetium are radioactive. Technetium 99 is one of the fission product of uranium, and it is beta emitter with half life of almost 10 to the power 5 years. It is obtained in kilogram quantities from the spent fuel rod from the reactor at nuclear power station. The rod may contain around 6% of technetium. These rods must be stored for several years to allow the short lived radioactive species to decay. Technetium has a no commercial use. Two of the isotopes of the technetium, 97 and 98, can be made by neutron bombarding of molybdenum. Some of the amount of technetium compound are sometimes injected into the patient to allow the radiographic scanning of the liver and other organs. So, before recording the X-rays or radiographic screening, we do inject some of the technetium isotopes. Rhenium is very rare element and occurs in the small amount on molybdenum sulfide ore. Rhenium is recovered as rhenium oxide from the flue dust from the roasting of these ores. It is used to make platinum rhenium alloy, which is having used in catalyst making low lead or lead free petrol. It is also used as a catalyst for hydrogenation and dehydrogenation reaction. Due to its high melting point, it is used in thermocouple, electric furnace, winding and in the mass spectrometer filaments. The next group comprises of two metal, namely ruthenium and osmium. Both are also very rare. They found in metallic state together with the platinum metal and coinage metal, that is copper, silver and gold. Abundance of element in the earth crust is also very low, that is to say for ruthenium it is just 0.0001 ppm and for osmium it is 0.005 ppm. The elements are both very scarce and expensive. Ruthenium is used to allow to form alloy with the palladium and platinum, and osmium also used to make hard alloy. All these metal have very specific catalytical properties. The next group we have a rhodium and iridium, the element having odd atomic number and having low abundance in the earth crust. As you can noted upon, the rhodium have only 0.001 ppm and iridium have 0.001 ppm abundance in the earth crust, and therefore they are very costly element. Rhodium and iridium are very hard metal. They are noble as well as unreactive. The iridium is having a density 22.61 gram per centimeter. Rhodium and iridium are resistant to acid, but they react with oxygen and halogen at very high temperature. Both of these elements have ability to form a large number of coordination complexes. The next group we have a nickel group, in which the two metal ion is palladium and platinum. Palladium and platinum are also a rare element. They are appreciably more abundant than other platinum group of metal, and palladium is in fact slightly more abundant than the platinum. But the important wise, platinum is being manufactured on a larger scale. Palladium and platinum are both rare and expensive. They are noble and not very reactive, but both of them are slightly more reactive than the other platinum group of metal. They are used widely in the field of catalysts, and most common oxidation state of palladium and platinum is +2, and for platinum other than +2, +4 oxidation state is also known. Both this absorbs hydrogen, and the amount of hydrogen absorbed depend on the physical state of the gaseous hydrogen. Platinum in +2 as well as +4 oxidation state are forming extremely large number of complexes. Palladium and platinum find extensive use in the field of catalysis. A new increasing use of a platinum in the three-way catalytical converter is well known, particularly in the vehicle. To control the pollution or to abate the pollution, the platinum catalyst is finding use. The next group we have a coinage metal, in which a two metal ion is silver and gold belonging to copper group, that is copper, silver and gold. The main use of silver is in form of their halide, that is AgCl and AgBr. They are useful in photographic emulsion. Silver is also important in the field of jewelry and ornaments, also batteries and silvering the mirror. Gold is also one of the important metal for jewelry and for the ornamental purpose. It is alloyed with a mixture of copper and silver. As you know, the pure gold is 24 karat, but the gold having a lower carat, namely 18, 22 or even 9 carat is also known. and the meaning of which, as you are aware, 18 karat gold means 18 part by weight is pure gold and remaining 6 part by weight is either copper or silver. The small amount of gold are used to make corrosion free electrical contacts. For example, on the computer board or thin film of the metal will reflect the unwanted heat from the sun in the summer. The liquid gold is used to decorate picture frame, glass and ceramic ornaments. The metal in the group have the highest electrical as well as thermal conductivity, and therefore, it is used in the conductivity purposes. It is most malleable and ductile and having very high enthalpy of sublimation and higher ionization energy. This is the reason why gold and silver is unreactive and showing a noble character. The metal have positive E0 value and are thus below hydrogen in the electrochemical series. Thus, they do not react with the water or liberate hydrogen with the acids. The last group, we have a cadmium and mercury placed in the zinc group, that is zinc, cadmium and mercury. Cadmium and mercury shows a few properties associated with typical transition element. This is because they have a completely filled D cell, which is not available for the bonding. Cadmium does not show variable valency, whereas mercury exists in +1 and +2 oxidation state. Most of the compound of these two metal ions are white because of the D10 electronic configuration. Some of the compound of mercury in +1 and cadmium in +2 oxidation state are colored due to charge transfer transition into them. The metals are soft compared to other transition metal, and this is because the d electron do not participate in the metallic bonding. The melting and boiling point are very low, and as we know that these metal are more reactive than the copper group, and even though the ionization energy for these two groups suggest the reverse trend. The exposed mercury surfaces should always be covered to prevent a vaporization and hence poisoning. The gas is unusual because it is monoatomic like a noble gas. Cadmium is used to protect steel from the corrosion. Cadmium absorbs very well neutron, and therefore, cadmium rods are useful in the nuclear reactor to absorb the neutron. Cadmium sulfide is used as a yellow pigment in the paint industry, and it is also used for the alkaline nickel cadmium storage battery. Mercury is used for the extraction of silver and gold in form of their amalgam. Even it is known to form various organomercury compound. For example, phenyl mercury acetate is fungicidal and germicidal in nature. Mercury chloride is used to treat clubroot, a disease in the brassicas, that is cabbage family plant, while HgCl2 is used to make organo derivative and HgO in anti-fouling paints for the ships, etc. Almost all the compounds of mercury are toxic, but the organic compound are extremely dangerous and have ecological effect. Small scale use of mercury includes thermometer, barometer and manometer. So, in summary, we have been introduced to the second and third transition series metal ion. We have seen their position in the periodic table. We have also seen the electronic configuration of second and third row transition metal ion, and we have been introduced to the general properties and some of the uses and applications of the second and third row transition metal ion. In the next lecture, I am going to give you few more important physical and chemical properties of these two rows transition metal ion.